In the last part of our session about stochastic inventory theory, we will be looking at the problem when we are dealing with a perishable item. The classical model for considering these kind of product characteristics is the Newsvendor problem that I want to introduce today to you. The problem that the Newsvendor is facing is that at the beginning of his selling period, he needs to order a quantity of newspapers, so he needs to have somehow an idea about the demand that he is facing, and this demand is uncertain. So he needs to predict it and to order accordingly the amount of newspapers. And the problem is that when he orders too many newspapers that he cannot sell, then he can just throw them back, or maybe he can give them back to the editor, so he would get a kind of a salvage value for the material that he's handling back. But the product itself, a newspaper, depreciates over the time, meaning that more and more the news become known to the people, then they are less prone to buy the newspaper from the Newsvendor. So more and more the day continues, the less value the newspaper will have, and the, let's say, the evening, the Newsvendor cannot sell the specific journal anymore if we are talking on daily newspapers, of course. So the problem that the Newsvendor is facing is he should estimate how much to purchase in before, and he wants to maximize, of course, his profit, while he needs to have an estimate about the demand that he is facing. Can be that, of course, he is experienced and he knows how many people and whom will stop by to buy a newspaper from him. But there can also be random demand from people that are just stopping by occasionally to him. So his decision variable is once again the order quantity. And now we don't need to think about the reorder point, because that is given. He needs to purchase his items in the beginning of the period, so that he's minimizing his expected cost that he incurs while buying the newspaper. Yeah, that's pretty much it. So we can look at maximizing his profits, but to maximize the margin, we can also look at minimizing the expected costs. Then we are also looking at extending his margin and the profits for him. This is normally how this is done with the Newsvendor problem. So we are minimizing the expected costs here. We are looking at the basic version of the problem at a single perishable item. There are also models available that deal with multiple perishable items. That makes sense if they are somehow linked to each other, so they would occupy capacity or something, so that these problems need to be regarded together. The Newsvendor is facing stochastic demand, so his demand is uncertain, and we are looking at a single period in a continuous model that is equivalent to the EOQ formula, to the stochastic one. We are looking at a single cycle and a single period, so that then we assume that it will repeat itself over and over again. The relevant costs that we need to determine are based on the ending inventory. So we look at the cost of having a positive inventory that remains after this period. We call them overage costs. So the cost of having too many newspapers that then needs to be given back somehow or scrapped. And we are looking at underage costs that are the costs of not having enough newspapers to sell to the customers so that they remain unsatisfied. The model that we are looking at can be graphically shown as follows. Here we depict the order quantity, and if we depict here the costs that I denote with G from dependent from the order quantity and the demand. So these are our total costs. Then we can, if we realize or we estimate certain demands that we depict here, then the cost of we have a certain cost for purchasing our items, and mainly that's not the cost function in itself, but it's showing you how the derivation of the cost function works. So if you're looking at D and we have ordered some order quantity Q here, then if we look at this interval, we can say that Q is less or equal to the demand. In this case, it's less, of course, but it can be less or equal to the demand. And then we have more demand that we have ordered newspapers. So in this phase, we would have too little newspapers. And that means that here we are facing, in this part, shortage costs. And if we look at the other part, if this is our realized demand and we have ordered a Q that is placed here, then we can state that D is smaller or also equal to the ordered quantity, and that means that here we have ordered too much newspapers. And here we would be facing a cost for inventory holding, or as we assume that we cannot sell the newspaper anymore after the period, then this would not be inventory holding, but a scrapping cost. So the cost that we incur of ordering too much. And here we can also see that if this number is positive, then we had too little newspapers ordered, and here, if this number is positive, then we have ordered too much. So now the good question is how much to order, so that the probability that the demand is less or equal to the demand that will be realized is minimized. Now we can state the expected cost function. As follows. So the cost function is named G, dependent from Q, and that is equal to the expected costs that are dependent about the order quantity and the stochastic demand. So when we consider our graphic, then we can state G from Q as the cost of having too much inventory or too much items bought. C from overage, so the cost of overage in the integral from 0 to infinite, and that is now given by the maximum value of either 0. So if we don't have overage costs, if we have not ordered too much, then this would be 0. And in case that we have ordered too much, we have our order quantity minus the realized demand, denoted by X. So what we will have been realized after the period, and this is Fx from dx. And now the cost of having too little inventory or too little newspapers ordered is from Q, from the order quantity to infinite. And here we take the maximum value of either 0 or the realized demand minus our Q. So if that value is positive, then and this is f from x dx for the integral. So if we have ordered too much, so demand minus Q is positive, then we have more demand that then we have more demand than we have ordered newspapers, and that means this value becomes here, or this term becomes positive. And if that is the case, then this could be 12 or any other value. And the maximum states that if one of the terms is higher, then we take this one into consideration for our integral and for the costs. So in case that we do not have ordered too little, then the value here would not be positive and we would take the 0. And this works for both sides, of course. So we can have either or. We can have either underage costs because we ordered too little, or we order too much, then we have overage costs. When now we do the, and one small thing, the cost function, this is just, the first one was to let you know how it works with respect to the costs, but the cost function will have a curve as follows. It will look like something like this. And then, of course, we want to order the Q that minimizes the costs. So this is where we find our optimal order quantity. And that would be the differentiation. We differentiate, of course, the cost function to with respect to Q. And this is then, we apply the rule of Leibniz. So this is then f from Q multiplied by the overage costs minus the costs for underage costs. So these are probabilities that we have ordered enough. And we can also, or what you should also consider is that we want to take the probability into account that our demand is smaller than our ordered quantity. Then we have overage costs, and this should be somehow balanced with the probability that we have underage costs, sorry. So these two probabilities should be balanced, because in the case that they are balanced, then we would operate exactly or order exactly as much as the demand that will occur, and then we would minimize our costs that we are facing as a news vendor. So if we take the last into consideration, or this one into consideration, and then we solve it for the probability after some algebra, we will get the following. So here we apply just some algebra to get the probability. So just extensively, here we lose the bracket. And then we can take this term on the other side. There we get CU from FK plus CU F from K, and on the other side we have the CU left. Here now you realize that we can make things a little easier, and our goal is to isolate for the FQ. So here, if we take that into brackets for multiplication, then we can get that on the other side, the term, and then we will have F from Q equals to the underage costs divided by overage cost plus underage cost. And this term here is called our critical ratio. Or also CR, because it denotes the probability that we can fulfill our demand. So this one is probability, so you will have it between 0 and 100%, or so if we take it into percent, or it's between 0 and 1, of course. And that gives us a metric of service level. So the higher this number is, the more we would be able in stochastic demand to satisfy our demand. So this gives us also here the probability as said that we will have enough newspapers to satisfy the realized demand when it will be realized. And as we are looking at this costs after the day or the time unit has been realized, then we will know how the demand has been given. If we go now back at the lecture slides, you will see that here we have derived the optimal solution for the Q. So this is here we have the derivation of the optimal costs. We differentiate the total cost function with respect to the Q. Then we set it to 0, and then we get the critical ratio, that is the probability to satisfy the demand. And if we go further, then we can derive the formula for the optimal Q. Then is then given if we have, needs to be said, we are assuming that we have a normally distributed demand with a mean and standard deviation. So let's take an example how this works, and let's take Holger's Newsstand. The Excel file is not provided at the moment, but we have the example. Assume for the demand that you would find out when you analyze the demand in the Excel file. Here we take a shortcut, and you will find that we have a mean of 11.73% for the demand. And we have a sigma of 4.74. The overage costs are not now given by the 25% purchasing costs, 25 cents purchasing costs. And then Holger gets a salvage value of 10 cents. So this we can get 15 cents for the overage costs. For the underage costs, so the cost of having too little, Holger loses his selling price if he has too little, and from that he can distract the purchasing price that gives his margin. So the underage cost in total is 50. And then we can calculate the critical ratio. That was the underage cost divided by the sum of underage and overage costs. And here this would be 50 divided 50 plus 15. And this in total is 0.767. So if we round up, 0.77. So that is the metric of the service level. Or the probability to satisfy demand. So he should buy enough copies to satisfy the weekly demand with a probability of 77%. So the optimal Q or order quantity is the 77th percentile of the demand distribution. And this we can see if we take the demand distribution. So we have a realized demand and we have the function from the demand that is normally distributed in our case. So here's the bell curve where we have a mean given here, and then we will have some order quantity, and then in this case here we have also our standard deviations. So this is when we have a plus standard deviation, for instance, and this is when we have a minus. Now our mean is 11.73, and here we have calculated now that we are at our critical ratio is 77%. So the optimal order quantity, Q star, is now given by the mean plus the value for Z multiplied by the standard deviation, and the Z for the 0.77 as we have to look it up at our distribution table. And if we do so, we have to find 77, and this is here at that value, and we see that our Z value is 0.74. So Z equals 0.74, and if we plug in our values, then we get the following order quantity, that is 15.24. So in total here we can round up because we want normally to have not too little or too much than too many. But in this case, it's sufficient to have 15 copies. So you've seen this is a quite simple and modest model. It works. It is very, very simple, but it works for quite a lot of items. You can imagine that newspapers are just one part of it, but you can apply it to everywhere where you have products that are just valid for a certain time period. This can be concert tickets, it can be flight tickets where you sell the price of a seat in a certain plane. It can be very different product. So it's quite an interesting and handy model. So if you have any questions regarding stochastic inventory management, then please drop a comment in the YouTube video section, or for my students, just write me. Okay, thanks for watching.